Think about what happens when you look at a fast, sloppy scribble on a piece of paper. Almost instantly, you know it's the number 3. Your brain processes that messy ink without you ever having to stop and calculate the exact angles or the curvature of the lines. You just look at it and you know. But if you sit down and try to write a traditional computer program to do the exact same thing, the task becomes daunting. Standard code relies on strict if and then rules. Writing a rigid set of mathematical rules to describe all the unpredictable ways a person might draw a 3 is practically impossible. Because a traditional calculator expects absolute perfection, the fuzzy variations of human handwriting trip it up entirely. To solve these kinds of messy, real-world problems, computer scientists realized they had to step away from strict calculators. Instead, they built software inspired by the structure of the human brain. They created neural networks. To see how a network handles a fuzzy problem like handwriting, we need to look at how it breaks down one massive challenge into hundreds of tiny, bite-sized decisions. Imagine the neural network as a towering office building that operates as a massive, multi-story detective agency. Its only job is to look at a single mystery image and figure out what number it is. On the ground floor, you have the input layer. Since the mystery image we're trying to solve is a grid of 28 by 28 pixels, we need 784 rookie detectives, one to watch over every individual spot. Each rookie has a highly restricted job, watching one specific pixel. If their pixel is pure white, they shout loudly, reporting a value of 1.0. If it's black, they stay completely quiet, reporting a 0. These rookies don't know what the big picture looks like. They blindly pass their shouting reports up to the second floor, which is populated by mid-level detectives. This is our first hidden layer. The mid-level detectives have a different job. They aren't looking at raw pixels. Instead, they listen to the rookies below them to hunt for specific visual patterns, like a horizontal edge or a small curve. This first handoff is how the network begins to organize the image. It takes a mass of raw visual noise and turns it into recognizable edges and shapes. So how does a second-floor detective actually decide if an edge is present just by listening to hundreds of shouting rookies? Connections represent weights, a measure of trust based on where rookies look. Positive weights increase the detective's confidence. Negative weights bring the score back down. They also use a bias threshold line, waiting in the dark until the score pushes past it. Once that threshold is crossed, the second-floor detective gets excited. They light up and pass their own specific findings up to the third floor. The third-floor detectives take these scattered edge reports and combine them into even larger concepts. They look for shapes like full loops or long vertical lines. Every hidden layer in the entire network is running this exact same operation. They weigh trust and hit thresholds, building increasingly complex ideas out of simple shapes. Finally, we arrive at the top floor of the agency, the output layer. There are exactly 10 chief detectives working here, named 0 through 9. In this final layer, the chiefs decide based on combinations of shapes reported from below. For example, if a loop up top and a curve at the bottom both come in hot, the chief for number 3 lights up, successfully solving the mystery. When you see the full process laid out, one thing becomes clear. The software does not have a conscious mind. It doesn't actually know what a 3 is. Instead, the network is simply a massive chain reaction. It is thousands of tiny mathematical checkpoints, all interacting with each other simultaneously. The architecture of AI succeeds by stacking thousands of these microscopic, simple decisions on top of each other until it finally makes sense of our messy, complicated world.